All right, class, we're gonna get started. So welcome back everyone from fall break. You saw I posted the grades for midterm 1 yesterday. So the average was 71, standard deviation of 12. The grades themselves should be posted to Canvas and accessible on Canvas, as well as on Gradescope, where you can see the rubric, which will tell you what the final answer was, and what the different elements were that I was looking for in how you set up your solutions to the problem. I guess one thing to note, if you're like below a standard deviation, below the average, you should probably come talk to me about how, strategies for how to, prepare for the next exam, and how to basically just how to do better on the next exam. I will be reaching out to a few of you to try to set up individual meetings. Yeah, if you're concerned, but especially if you're a standard deviation below average, then please do reach out to me, okay? Another reminder, welcome back from break. Homework 6 is due on Wednesday. I gave that one out on Friday just before break, and we'll have it due on Wednesday. Any questions about anything else before we get started? Yes. Yeah, that's pretty typical for the first midterm in this class. I think last year was around a 70, this year 71. Yeah. I expect the average student to get a B in the class. So average in this class will be about a B. Curve to historical average in the final.
So then would an A be like a standard deviation above or a little higher?
I'm not positive.
Okay.
Probably, yeah. So does the average go down with following midterms? No, this is about typical for a midterm. This is about where I'm trying to get the midterm to. Is about a 70 average or so at least. Yeah. Yep. I'm looking for groupings that are so I'm trying to make sure that you're not going to miss out on a letter grade by like a quarter of a point at the end. So I look for kind of natural groupings with big spaces between them to define my letter grade cutoffs. Looking at the entire class. Yeah, so I just put out all the numbers, like no names or anything, just all numbers, and just try to see where everyone sits. No, I don't do anything like that. There's no redemption or something, or throw away a grade. With the homework, you can throw away 2 grades, right? But there's nothing like that with the midterms here. Yeah. Okay. Any other questions? Okay. Great. So today we're going to begin our discussion of internal flows. So we're in chapter 6 now. I guess one of the things that I meant to do over break and I didn't have a chance to do was to make the readings more specific. That was a request from one of you to say exactly which sections to look at. That is still on my list, but we're going to be in chapter 6. Chapter 6 is where we're going to spend the most time of any of the chapters in our text. This is a topic of particular importance for chemical engineers. And in some sense, this is kind of what we've been building to from pretty much the entire class, right? So chapter 1, we went over definitions of different concepts in fluid mechanics. We've been using those throughout. Then we moved into fluid statics. That's how we understand pressure, and pressure is going to be really important here. We're going to use concepts from fluid statics and understanding what pressure head is, which is going to be really important for understanding pipe flow networks. Chapter 3 was our control volume analysis, and we're going to see that energy balance is going to be a primary tool in our arsenal for understanding internal flows. Chapter 4, we had differential equations. We're going to use that to understand velocity profiles in internal flows. And chapter 5, our scaling analysis, is going to come back today as we just try to get a handle on variables that are involved. So we've been building tools basically all throughout the class up until this fall break that we're now going to use to understand flow inside of pipes and ducts and that kind of thing, right? So this is internal flows in chapter 6. One important concept that we're going to see over and over again from here on in the class is that of flow regimes. We've alluded to this a little bit, but we're going to talk about this much more specifically starting really in this chapter, continuing into the next one. And this has to do with basically Reynolds number in the flow. So let's imagine that we have a flow. So what we have here is images of flow through a pipe where you can see the top and bottom walls of that pipe. Get my cursor over here. So we have a top wall and a bottom wall of the pipe, and then we're injecting a dye into the pipe and watching what happens as that dye advects downstream. And so in that top flow there, we have a laminar flow. We're going to talk probably on Wednesday about what that velocity profile looks like. But if in laminar flow, we end up with essentially layers of velocity that basically don't mix with one another. They only mix by molecular diffusion. The only mixing would be by molecular diffusion. And so we end up with a nice steady stream of that dye moving through the center of the channel. But now if we imagine in this pipe flow, we turn up the velocity, and we saw this in a video example on a YouTube Friday before the break as well. But if we turn up that velocity, we start to see the formation of these little turbulent puff things, right? These little vortices that are starting to randomly appear and chaotically move downstream, chaotically develop as they move downstream. This is what we would call the transitional regime, because we are transitioning from laminar to what's next. If we turn the flow up even further, we're going to get to a turbulent flow. And now in this experiment, we would see just the steady creation and evolution of vortices within this stream. And if we turn the velocity up still further, we're still in that turbulent regime. This is probably the most important thing to keep in mind when we're understanding what's going on in pipe flow. And this idea of like what we see in laminar flow is very different from what we see in turbulent flow. And this is going to be a key preoccupation of us in chapter 6, is trying to understand, we're trying to develop tools that we can use to understand both what's going on, or first what's going on in laminar flow rather, and then what's going on in turbulent flow. And so again, the most important thing to keep in mind is Reynolds number, right? Rho u d over mu. We're going to see that in internal flow, we're generally going to define Reynolds number based on the diameter of the pipe. If we have a round pipe, if we have a square pipe, we'll get into what the definition of D is going to be for a square pipe. But typically we're going to use diameter as a length scale, not the length of the pipe. Okay, we're not going to use the length of the pipe. We're going to use the diameter of the pipe. This Reynolds number is the most important thing to keep in mind, right? The most important thing to know. Said it before, say it again. You'll hear from me in the future as well. If you don't know the Reynolds number, you don't know much about the flow, right? If you don't know the Reynolds number, you don't know whether you have laminar flow or turbulent flow, or if you're in this kind of messy transitional region in the middle. So Reynolds number is what's going to tell us that. As we increase the Reynolds number, right? In this example, imagine we have the same experimental setup and we're increasing velocity. So Reynolds number is increasing as we move from top to bottom here. And so the Reynolds number is what's going to tell us if we have laminar or turbulent flow. So we'll talk about cutoffs and what happened, a little bit about what happens at transition, although transition to turbulence is something that remains poorly understood in an active area of research. But some of the characteristics of laminar and turbulent flow. So in laminar flow, we have layers or lamina of fluid that move past one another with no mixing, right? So if we look at so this would be like flow out of a hose nozzle that's slow, and you've probably all seen this, right? If you take flow out of a faucet, or next time you turn on a faucet, look at this for yourself. Turn on like really slow flow, and you can see this nice smooth flow out of that faucet. That's laminar flow. And so here we're visualizing laminar flow coming out of a faucet that's horizontal, or a hose that's horizontal. And you can see these nice smooth layers of fluid that are basically just moving past one another without mixing. there's a really cool consequence of this if we go to ultra low Reynolds number, which is, calling it possibly my favorite fluids experiment. We'll watch it on Friday, where this is the before. So at the start of the experiment, he put in dye in different streaks, mixed it up, and then unmixed it because the Reynolds number is just crazy low. But we'll talk about that on Friday. But in laminar flow, and that's only possible at incredibly low Reynolds numbers, not the kind of Reynolds numbers we typically see in pipe flow. But to get back to laminar flow, it's generally fairly straightforward to solve computationally. Even if you have some complex geometry, we can generally solve it computationally fairly easily. We can often even solve it analytically. So we'll look at, you've already actually looked at analytical solutions to laminar flow without knowing it, maybe within a pipe. Or between two flat plates where we solve for the parabolic velocity profile. That is a velocity profile in laminar flow. So we can often solve for laminar flow velocity profiles analytically. And we are going to be doing so primarily on Wednesday this week. So in contrast, in turbulent flow, we end up with the characteristic of turbulent flow is that we have eddies across many different length scales, such that large eddies in the flow are transferring energy into smaller eddies and smaller eddies and smaller eddies until the point where the smallest eddies within the flow are dissipating energy into viscosity, into viscous drag, into friction, into heat. And you can see that so this is, the big red spot, Jupiter. So this is an atmospheric scale flow on a planet that is many times larger than ours. And you can see, if you look at this, you can see eddies of all varying sizes. Like if you just pick an eddy and watch it as it moves downstream, like pick this eddy and watch it as it moves downstream, you can see it essentially interacting with other eddies and creating still other smaller eddies through that interaction. And if you were able to zoom in on those smaller eddies that are created by this big one, you'd see it creating smaller eddies still. This has many characteristics of fractals, right? In that there's a sort of scale invariance here. Many deep connections to fractals in turbulence. And the characteristic of turbulence is most famously described in this poem. It's a little bit of poetry to start your second half of the semester. Big whirls have little whirls which feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. But it's describing fundamentally what's going on within turbulent flow, which is that large vortices are creating slightly smaller vortices. Those smaller vortices create smaller vortices still. And this happens, this is called an energy cascade. This cascade of energy happens all the way down to the smallest little vortices that are then dissipated by viscosity into heat and friction. And that is what characterizes turbulence. So this is definitely turbulence. What we'll see, or I guess what I'll tell you, we will deal a little bit with turbulence and start to approach the problem analytically. So you will see this. Turbulence in general can be very difficult to solve computationally, and it is currently impossible to solve analytically. So we do not have an analytical solution to turbulence. Part of this gets back to that Millennium Prize we talked about. That there are certain, there's a potential for certain mathematical singularities in the equations of motion describing turbulence. So even though this kind of flow, we could describe turbulent flow, certainly with this kind of character, using the Navier-Stokes equations. Right, so we know the equations, but we do not have a closed form solution to turbulent flow. So we're going to turn to empirical relationships to understand what's going on here. So just a note on the transition to turbulence, and this is going to come up many times over the next month or so, or 2 months. We're going to, one of the key things that we need to keep in mind, right, and one of the reasons that we need to understand what the Reynolds number is, right, in a given flow, is to know whether we have a laminar, transitional, or turbulent flow. And so there are 2 key numbers that you're going to need to keep in mind for trying to figure out, for taking your Reynolds number and trying to figure out whether the flow is laminar or turbulent. So for internal flow, the transitional Reynolds number, somewhere around 2300, somewhere around 2000, 2300. In practice, in a really, really good experiment, like with really, really a clean experimental setup and very low noise, and certainly none of this air conditioner noise, and that kind of thing. A transitional Reynolds number from laminar to turbulent of up to 10,000 or so can be observed in a laboratory condition. Under really noisy conditions, transition to turbulence can occur earlier. So if there are already a lot of fluctuations, or if you're taking your experimental device and shaking it around a lot or something, then you can see transition earlier than 2000 or 2300. But in general, we'll use somewhere around about 2300 as the transitional Reynolds number for the onset of turbulence for internal flow. The next chapter is going to be external flow. I just want to introduce this concept to you now because it's otherwise something that can trip you up. You go around believing that transitional Reynolds number is always 2300, and then I spring on you that it's different in external flow. That can sometimes cause confusion. But in external flow, the transitional Reynolds number is going to be around 500,000, right? So substantially larger. So a little point on this. Turbulence in internal or external flow is fundamentally the same. It's described by the same equations, right? We can describe it by the Navier-Stokes equations. If we were to look at, this is a little cube that was simulated computationally by Tony Saad's research group here at University of Utah. This is a cube of, so we simulate a cube of isotropic turbulence. So turbulence where, we're very deep within the flow, deep within a turbulent flow. And there's, we're far away from the boundaries, far enough away from the boundaries that there's no substantial gradients of velocity across this in any direction, but yet we have turbulent flow. This little cube could be someplace in an internal flow, it could be someplace in an external flow. It would describe the turbulence in either situation. So the turbulence is fundamentally the same. So a lot of the things that we're going to develop in this chapter to talk about turbulence, we're going to use in the next chapter to talk about turbulence. But one question is, why are the Reynolds numbers, transitional Reynolds numbers, different? One way to think of it is that internal flows use the pipe diameter in the definition of when the transition occurs. So we often write the Reynolds number for internal flows as RE sub D, because the length scale we use is the pipe diameter. And the pipe diameter is transverse to the flow, right? So the pipe diameter is perpendicular to the flow. So if I flow downstream, I have pipe diameter is transverse to the flow. In what we'll see in external flows is that we typically use the object length. So if we have flow over an airfoil, right, an airplane wing or something, we'll use like the length of the wing along the direction of the flow. And so we'll typically denote the Reynolds number in external flows, next chapter, as RE sub L. And this length is along the flow. And so the length scales are in different directions relative to the flow. And so we end up with a different transitional Reynolds number, essentially defining when we have laminar versus turbulent flow. Okay. Yes. Yeah, internal flow. Yeah, sorry. Internal flow means flow, yeah, within confined flow within a pipe or a duct, right? So flow within the air conditioning duct, that would be internal flow. Flow within a pipe, that would be an internal flow. External flow would be, yeah, flow around an airplane wing, flow around a wind turbine blade, flow around a car or something on the highway. Yeah, good question. Yeah, other questions about this? Yeah. Yeah, a river, we tend to actually call its own thing called open channel flow, because when you're dealing with a river, then you have the free surface at the top, and actually really strange things, interesting but strange things can happen. Like when you, if you reduce the width of a river, right? You would think by mass conservation, the height, the depth of the river would have to go up, right, in order to preserve the same flow rate. But actually, what generally happens if you reduce the width is that the elevation actually goes down. The height of the river actually goes down because when you reduce it, the flow speeds up, and therefore it actually needs less area to move through. So you get all kinds of counterintuitive things. So that's kind of its own area, which we are not covering in this class. That would be covered in a civil class most typically. It is in your text. So, and if you're interested, happy to talk about it. Yeah, good question. But a river flow would share some characteristics of internal flow, right? Because you have at least confinement on three sides. Yeah. So you would need this to study that. Okay, any other questions? Okay. So in internal flows, another distinction here is that in internal flows, we're generally going to have either fully turbulent or fully laminar flows. We'll talk about why we're going to try to avoid the transitional region as much as possible in internal flows. Generally, we're going to speak of a flow as being either one or the other. And so we have this transitional regime of Reynolds number about 1,000 to about 10,000 or so, or 5,000 or so. And I don't know, my warning is there be dragons. So in this region, we get a sharply different behavior, but predicting exactly when you get a shift from laminar to turbulent flow. Again, it's a subject of very active research. Depends on all kinds of things. And so if it's really important that you know exactly what the pressure drop is, for example, across a pipe, you should probably avoid the transitional flow regime if you can. Another difference, and again, we'll hit on this in chapter 7. I just want to set it up for you so it's not a surprise. In external flows, we can have regions of laminar and turbulent flow at the same time in the same problem. So in external flows, we generally can't avoid the transition from laminar to turbulence. One way we deal with it as engineers is actually by tripping flow to turbulence in external flows. Yeah. The transitional regime, this would be for internal flow. So 10,000, so about 1,000, right, to about 10,000, somewhere in here. We're in the transitional regime. It's around that 2,300. It is very broad. Yeah, I mean, the, what's that? 2,300 is where it is often observed in experiments. Okay. But it can be observed up to 10,000. We can have transition up to 10,000. And we can have transition down to 1,000. So yeah, there's a broad transitional regime. This is part of the challenge. So if there were one number, if there were one Reynolds number where we always see transition from laminar to turbulent flow, then it wouldn't be that hard of a problem. We could just define it experimentally, right? Define what happens experimentally, and then just follow that curve, right? Doesn't matter the shape of the curve. If we know the curve, we're fine, right? But part of the problem is not only the curve becomes a weird shape, so we'll talk about what curve I'm talking about, but the curve becomes a weird shape. The curve describing what happens becomes a weird shape, and we don't know exactly where it's going to happen. So a famous example is, and then sorry, I see a question in the back. So a famous example, I showed some images of this experiment of like putting dye in a pipe and watching the flow of the dye to try to figure out where the transition is from laminar to turbulent flow. Most of the time when you run this, you get a number for transition to turbulence of somewhere around 2,000, 2,300, 2,000, something like that. Reynolds, of Reynolds number fame, famously ran and reported on this experiment, possibly first, right? He's the one whose name is on the number. He very famously ran this experiment. And he was able to get transition to turbulence up to something like 12,000, Reynolds number of 12,000. But when you go, and his experimental apparatus still exists, right? This is over 130 years ago. The experimental apparatus still exists at his lab in England. And if you go there now and try to run the same experiment on the same apparatus, you get a transitional Reynolds number closer to 2,000. Partly because, you know, maybe things, maybe there's more roughness on the inside of pipes or something, so there's more disturbance caused by that. There's also a lot more traffic now than there was 130 years ago. You know, bigger trucks outside causing vibrations in the fluid that create disturbances that cause transition to turbulence sooner. So, yeah, when I say there be dragons, I mean like it is a confusing. It is a someplace that is that can confound your best efforts as an engineer to try to control. So. Just take no stance on that. Yeah, so but even that, even people just walking around, right, and you know, around outside of your experimental apparatus or next to your water pipe. I mean, that all this would be a lot cleaner. Yeah. So yeah, this is so I guess another thing that we're going to see here, maybe to this point in your engineering careers, you know, you're used to maybe one answer. Each problem has one answer, and there's a number, and we say what that number is. We're going to see that for some of the important correlations that we're going to use here, we'll do problems, and our answers are only going to be good to about 10 or 15%. So, you know, I kind of harp on significant digits a little bit. I know many of your engineering professors do, but it's especially important when we're talking about some of these flow problems where, yeah, your answer is only so good. So we're going to look at, you know, some different correlations, different curve fits to, for example, turbulent flow, and that's for the turbulent flow regime where we have some idea or some hope of coming up with an answer. We're going to have answers that are only good to within about 10 or 15%. So if you give me an answer to one of those problems to, you know, 10 significant digits, because that's what your calculator gave you, it's wrong in a very fundamental sense, right? Even if you have, you know, a number that's in the right ballpark, you know, expressing it with such high confidence is wrong in a very real way. Okay. So yes, this is uncertainty. This is massive uncertainty, but this is reality, right? This is what physics gave us, and this is what we as engineers have to deal with. And we will see a similarly broad transitional regime in external flow as well. We're generally, there's an important concept, which is that of fully developed pipe flow. So if we consider, we have some opening, like let's say we have a giant tank out here on this side, and we have a pipe connected to that tank, and we now have flow into that pipe. You can imagine that as let's say it's water, as that water is flowing into this pipe, right? The velocity profile of the water is going to be changing as we move downstream. So if let's say we end up with laminar flow, we're going to have we'll see that we have a parabolic velocity profile at some point downstream. But that parabolic velocity profile doesn't just jump into existence at the beginning of the pipe. It takes some time to, we would say, develop, to go from what would look like probably pretty uniform flow at the entrance to this parabolic flow further downstream. We will often, when we're solving problems, only consider the case of fully developed, but let's just talk about why that is. In this entrance, in this entrance region, what's happening is that basically the influence of the walls, the viscous influence of the walls, the drag that the walls exert on the flow, is kind of creeping outwards into, as we move downstream, it's creeping outwards into the flow. And so the viscous influence, the region of viscous influence grows with distance into the pipe. And that's what's shown by these dashed lines here. That's the region of the pipe flow that's been affected by the wall, by the drag from the wall. When we say we're fully developed, we mean that the flow velocity profile is constant with distance into the pipe, meaning, so through this region here, we have the velocity profile, the viscous influence is growing, right? The walls, the influence of the wall is growing into the center, towards the center of the pipe, and the velocity profile is changing from fully uniform to parabolic downstream. Right, so this is the developing region. But when we're in the fully developed region, the velocity profile is now constant down the pipe and stops changing. So once we get to here, then, if we make this pipe a mile long and we look at the velocity profile a mile down the pipe, we should see the same velocity profile that we had here. Once we're in that fully developed region. And so at this point, if X is our coordinate down the pipe, right? If we put X on here, we define X, oh, there it is. X is our direction down the pipe. Then at this point, ddx, right, the partial derivative of, for example, our velocities with respect to X are going to be equal to 0. Yeah. Yeah, so it starts out at not parabolic. I mean, out here, right, you're going to have velocity vectors looking something like this, right? And then at the point where it meets the pipe, they do not instantly turn into a parabola, basically. It takes some time. Well, at least, so let's see, if we imagine we're right here, we'd have straight right across the center and then it just barely decaying back. So right out here, yeah, we'd have flow coming in from some angle. But once we get into the pipe itself, it's all going to be aligned with the pipe. Yeah. Yeah, I mean, the no slip condition applies out here as well. But yeah, the no slip condition, yeah. So this is essentially the influence. Another way to think of this is the influence of the no slip condition, right? Of the velocity of the fluid being 0 at the wall. That influence of no slip is growing with distance down the pipe. Until basically the influence, let's say, from the top and bottom walls meets, right? And then we have this fully developed flow. Yeah. We will look at the equivalent of diameter, or how to define the equivalent of diameter for a rectangular duct or something as well. But but we can define something that has same dimensions of length. We'll call it hydraulic diameter. And we could use it to describe a square duct or something, right? So if you wanted to understand air conditioning, right, where we have often square ducts, we can use that kind of thing. Yeah, good question. Okay. So in this developed region, we have ddx equal to 0. We can understand something. So without getting into like the full solution to what's going on here, we can learn something about development of flow using dimensional analysis. So this is going to be a tool that we're going to use, again, quite a bit in setting up the concepts in this chapter, because it lets us say something real about the problem without getting into all of the physics. So if we say that we want to know what this entrance length is, we can say that entrance length, in general, we expect to be a function of the pipe diameter, the velocity of the flow, density, viscosity. So we have how many dimensionless groups should describe this problem? Okay, how many variables do I have? 5, okay. How many dimensions are there here? Maybe a hand for 1 dimension, a hand for 2 dimensions, a hand for 3 dimensions, a hand for 4 dimensions. No, right? Mass, length, time, right, are going to be described. Okay, so how many variables do I have? So sorry, 5 variables, 3 dimensions. How many dimensionless numbers do I have? 2. Yeah. Okay. So we're going to have 2 dimensionless variables describing this. Can anyone tell me one of those? Reynolds number. Yeah. How do you know Reynolds number? Good guess. Yeah. Well, if you look, we have, we could set, we could do the same trick of setting like one of our secondary variables as rho or something, and we would end up with Reynolds number come out, right? Yeah. So Reynolds number. Does anyone know what the other one is going to be? I guess you have slides in front of you, some of you, but what would the other one be? Yeah. L over D. Yeah, would be a great one. Yep. There you go. So two-dimensionless groups. And these are typically L over D and Reynolds number. Okay. So for laminar flow, L over D, the entrance length over the pipe diameter is generally about 0.06 times the Reynolds number. And in turbulent flow, L over D is generally about 1.6 times Reynolds number to the 0.25 power, where Reynolds number less than 10 to the 7th. But this means that L over D is typically less than about 100, often much less than that. So for a 2-inch pipe, so if we have a 2-inch diameter pipe, our entrance effects are only within the first 16 feet and often less than this, often a smaller distance than this. So we're generally going to ignore the entrance length effects within our problems. So in practice, we can often ignore them. In some cases, they will be important, and we're going to lump them into something we're going to call a minor loss later on in chapter 6. So we will come up with a sort of an engineering approximation to include these effects, but we're going to discuss that later in the chapter. Okay, so we're generally going to consider fully developed flow, and the approach that we're going to be using in this chapter, as I said, is an energy balance. All right, so we're going to come back to this. So when we have steady flow in a pipe, we can apply energy balance as what comes in is equal to what goes out, right? So on the inlet, we have our ability to do pressure work, our kinetic energy, our potential energy, the same in the outflow. Frictional losses, that's an out. Pump, that's an in, so we get a negative sign on this side. And if we have a turbine that we're turning with the flow, that's an output as well, energy output as well. Need a grounding strap or something. So we're going to start with pipes. We'll consider pumps, and we'll have problems where we try to find the energy input or the power input of pumps. But to start with, we're going to ignore pumps and turbines and just talk about pipes themselves. So we're just going to have flow energy in is equal to flow energy out plus H friction, or loss due to friction. And note that this is almost the Bernoulli equation, right? We didn't have this frictional term, then we just have Bernoulli, right? But this frictional term is actually going to be most of your problem solving in chapter 6. Is going to be about defining what this frictional term is. You cannot leave this out, okay? So it is not, it's really an energy balance. Sometimes you'll see this expression called like an engineering Bernoulli or a modified Bernoulli equation, but it is not strictly the Bernoulli equation. It's Bernoulli equation plus this term, or more properly, an energy balance, right? So this is an energy balance. Yes?
For the density.
No, sorry, the alpha term is can anyone explain, what is the alpha term again? Correction factor. Yep, exactly. So it's because in general, in pipe flow, we have non-uniform velocity profiles, right? And so we have that correction factor. We're going to see it's actually going to drop out, but we'll get there in a second. So it's almost Bernoulli, but we left in the head loss due to friction. And we need to account for this correction factor in general in this expression. But in fully developed flow, V in is V out, right? So if we have a pipe, the pipe is not changing in area, and that's often going to be the case that we consider. By mass conservation, the velocity in is equal to the velocity out, right? Average velocity in is the average velocity out. And if the velocity profile is not changing, then everything about that inflow velocity profile is the same as the outflow velocity profile. And so these terms actually drop out. And so what we end up with, so in a rearranged form here, is the head loss due to friction is the Z1 minus Z2 plus P1 over rho G minus P2 over rho G. Okay, so velocity dropped out of, or these velocities dropped out. Now the question is, what is this HF? Right, and this is again the question of chapter 6: is what is HF? We're going to be talking about this throughout the chapter. Might have lost it. There we go. And this, just before we move on, this Z plus P over rho G, if this is dimensionally consistent, what are the dimensions of P over rho G? What are the dimensions of P over rho G? It has to be length. If this is dimensionally consistent, and I hope it is, I hope I haven't made that mistake, then this P over rho G has to have the same dimensions as Z, and Z is just height. So this has dimensions of length, right? So this thing is sometimes called the hydraulic grade line, or HGL. We'll see an example of this, I think maybe next YouTube Friday, once we've gotten a little bit more stuck into solving some pipe flow problems. We'll see an example of why we use this and why this is convenient. But that is sometimes called hydraulic grade line. So in your textbook, looks at the question of how do we define what this HF thing is. And if you actually use momentum balance approach, right, again, chapter 3, you can derive an expression for HF as 4 times the length times tau wall, the shear stress at the wall, the shear force basically being applied by the wall on the fluid, that's tau wall, tau W, over rho GD. So now the question is like, well, what's tau wall, right? We know tau wall, we know HF. But we don't, the problem is that we don't always know what tau wall is. So we'll see in the laminar case, we can solve for this directly. But in the turbulent case, we're not gonna be able to solve for tau wall directly. So we're gonna have to use empirical relationships. And so recognizing this problem in 1850, Hagen noted that HF goes as about V squared when you're looking at turbulent flow. The head loss due to friction, the frictional loss within a pipe increases with about the square of velocity. And so we proposed this following relationship, which we're going to use quite a bit for the head loss due to friction. Friction factor F is going to be now some unknown empirical constant times L over D times V squared over 2G. I should have boxed this and put this in red and bold, but we're going to be using this over and over and over again in chapter 6. Okay. So remember from last slide, we said that the most of chapter 6 is going to be about defining HF. Well, now we've kicked the can a little bit further down the road, and now we're saying that we need to figure out what F is, what this little friction factor F is. It's going to be, most of our problem solving is going to concern that. This V is V average. Yes, that's correct. This V is V average. That's correct. And this D is diameter, and L is the length of the pipe. Right. So longer pipe, bigger frictional loss. Right. Higher velocity, bigger frictional loss. Smaller pipe, bigger frictional loss. So we still use this today. We will be using this in class. In this class. In this definition, so this is something to be careful of. In this definition, which your textbook uses, this F is called the Darcy friction factor. But something you need to be aware of is that sometimes the fanning friction factor, and within a chemical engineering context, this is sometimes used as well. Sometimes you'll see friction factors that are the fanning friction factor instead. And you can convert between the two. So the Darcy friction factor is just 4 times the fanning friction factor. Okay. So your textbook does everything in terms of this Darcy friction factor. But just be aware, if you see an F quoted someplace, you need to understand, is it Darcy or fanning? Okay. Again, in your textbook, it's going to be Darcy. But that is not always the case. So there's this, convention, weird convention between the two. Okay. Yeah, there's something definitely to be aware of. Okay. Yes. This is HF. Oh, HF goes as V squared. So HF scales as V squared. HF increases as velocity squared. That's what that means. Yep. Yeah, it's a little tilde meaning. Yeah. It's a way of writing out like how something scales, right? Or how one variable. Yeah. Okay. 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 So so F is, we're going to solve analytically for F on Wednesday in laminar flow, but in turbulent flow, we can again use scaling analysis to understand something important about F. We'll start out we'll define the problem in terms of tau wall. We'll say that tau wall in general is a function. Actually, this is an example that we did in chapter 5. We said that the shear stress at the wall is a function of distance down the pipe, pipe diameter, velocity, density, viscosity, and epsilon, which is the roughness of the wall. And we get that, we know that dependence from experiments, right? For example, starting with Hagen and even before, we know that those are the things that this problem depends on. In chapter 5, we found 4 pi groups for this problem. And here we're going to simplify a little bit, noting that if for the case of fully developed flow, this X variable drops out, so we lose a pi group, and we just have 3 pi groups left. Reynolds number, epsilon over D, and tau wall over rho V squared. We also know that HF is equal to this. Hagen defined the friction factor F. This expression here is basically a definition of what friction factor is. But Hagen defines friction factor in this expression here. And so we can now relate tau wall to F, our friction factor. Yep. Can someone explain why the 3rd pi group drops out? Francisco? Because we're considering fully developed flow, right? So if we consider fully developed flow, then this problem is no longer a function of X, right? Or ddx is equal to 0, right? And so we can drop out this pi group. Good question. Okay. So we can write this expression for HF. So F is 8 tau wall over rho V squared. So the dimensions, so F is dimensionless. Our friction factor F is dimensionless. Something we learned here. So the last pi group, this pi group is generally just written as F. So now the question is, how do we figure out the friction factor? And we're going to see that we can solve for that friction factor F analytically using laminar flow. And that's going to be Wednesday's class. And for turbulent flow, we're going to have to do this experimentally. So this is the Moody chart. We're going to see this many, many times over the course of this chapter. It has a line for laminar flow, a nice straight line for laminar flow that we're going to derive on Wednesday. And then this big tangle, this big mess, they're actually not tangled, this big mess for turbulent flow. And these are essentially defined experimentally. And that's going to be the point of a lot of this chapter. If we have non-standard pipe designs, we can do this computationally. Yeah, most of this chapter is going to be about finding F using some approaches like this. All right. Thank you all. See you on Wednesday.